Welcome to my video lecture. This is N.Amarnath, Assistant Professor in Mathematics, Department of Humanities and Sciences, MLR Institute of Technology. Under the course Linear Algebra and Calculus, I am going to deal the quadratic forms topic. In that topic, we have reduction of quadratic form to canonical form by orthogonal transformation. This topic I am going to deal. In the previous lecture, we have discussed about the canonical form and what do you mean by canonical form, how to write and properties related to quadratic form such as rank, index, signature and nature of the quadratic form. That all we discussed very clearly. In this lecture, there we are going to discuss the reduction of quadratic form to canonical form. Canonical form by the orthogonal transformation. Then quadratic form, it is a second degree polynomial, canonical form is a second degree polynomial. What is the difference? Quadratic form can have square terms and product terms, but whereas the canonical form have only square terms. Generally quadratic form we are writing x transpose ax. Quadratic form, canonical form means y transpose dy. See, both are the square terms only, both are the second degree terms and homogeneous. Then it is a transformation happening the x variables to y variables through a transformation. Here we are calling as the x is equal to py, that we are going to discuss in this lecture. Now, so here I am giving the working rule, the methodology to reduce the quadratic form to canonical form using the present method orthogonal transformation, orthogonal reduction. We have some other reductions also, using diagonalization we have, using Lagrange's method also we have, but in this lecture I am restricted for orthogonal transformation, right? So one quadratic form will be given to us, then the question is reduce the quadratic form to canonical form by orthogonal transformation. Means our transformation must be orthogonal. That means the matrix involved in the transformation must be orthogonal. That is the transformation. Here I said now x is equal to py, x we are converting to y through the matrix P. Here this P must be orthogonal. Then only it is called as orthogonal reduction, our procedure. Already earlier we discussed about the video lecture, if it is symmetric matrix, how to convert into the diagonalization using orthogonal reduction. Same process will be followed, but here additionally what we have, canonical form and orthogonal transformation. Till this diagonalization we have discussed very clearly. Let me explain again what is the procedure. So one quadratic form will be given, x transpose ax. For the quadratic form, first step, change the matrix to symmetric matrix A. We know from the square terms we write along the principal diagonal, remaining product terms coefficient divided by 2, write in the proper position, that will be the symmetric matrix. Find the eigenvalues and eigenvectors of the matrix. For the matrix we know very well how to find eigenvalues, eigenvectors, that we do. Suppose generally we have 3 by 3 matrices, 2 by 2 also. 3 by 3 we get 3 eigenvalues and 3 corresponding eigenvectors. So that I am writing here corresponding eigenvectors for each eigenvalue. Lambda 1, 1 eigenvector, lambda 2, x1, and lambda 2, x2, lambda 3, x3. So we will find eigenvalues lambda 1, lambda 2, lambda 3 as well as corresponding eigenvectors x1, x2, x3. Next step, since our reduction is orthogonal reduction, we should verify orthogonality of the vectors. Each vector and each pair of the vector x1 and x2, x2 and x3, x1 and x3 are orthogonal or not, we have to check. Mutually orthogonal, that we discussed. How can we say that vectors are orthogonal to each other? Then orthogonal to if their dot product is 0. Dot product means, let us have x1 is equal to 1, 0, 1. Suppose x2 is equal to, we have 0, minus 2, 0. See, dot product x1 transpose x2 means for the multiplication purpose we can transpose any one of the vector. 1 into 0, 0, 0 into minus 2, 0, 1 into 0, that is 0. then these two are orthogonal. X1 and X2 are orthogonal to each other. Such a way, we have to verify the obtained three eigenvectors are orthogonal or not. If not orthogonal, we have to make them orthogonal by changing the values. So we need to prepare the eigenvectors such a way three are mutual to orthogonal, right? That we have done in the symmetric matrix reduction. Again, we will do here. So form model matrix P with normalized eigenvectors which becomes orthogonal. Normalized eigenvectors in the sense each vector is divided by its norm. So x1 by its norm x1. That is called normalized eigenvector x1 cap. Similarly, x2 cap, x2 by norm x2, x3 cap, x3 by norm x3. What is the norm? Means length of the vector. Suppose x1 is there, 1, 0, 1. What is the length of this vector x1 norm is equal to under root of sum of the squares of the quantities of the vector 1 square plus 0 square, 1 square plus 0 square plus 1 square, which is equal to root 2. This is called length. What is x1 cap? Then 1 by root 2, 0 by root 2, 1. And each value of each component of the vector divided with its norm, with length. That is called normalized eigenvector. So, we need to form model matrix P which contains x1 cap, x2 cap, x3 cap, which are orthogonal to each other. Automatically, P matrix will become orthogonal. What is the advantage we have orthogonal? If it is a P orthogonal, we can have P inverse is equal to P transpose. Simply transpose the elements, then you will get the inverse. Because in diagonalization, we need a inverse of the matrix. P inverse AP is equal to T. That is called diagonalization. So, P inverse AP is equal to D. This is a diagonalization formula. So, already we got P inverse transposing we got. Multiply these three matrices P inverse AP into D, you will get diagonal matrix which contains only eigenvalues in the principal diagonal. That is D of diagonal matrix means diagonal of lambda 1, lambda 2, lambda 3. And exactly in the principal diagonal you will get the eigenvalues, remaining elements become 0. So we got the diagonal matrix. Then canonical form. What is the canonical form formula? Y transpose dy. So y is the column matrix we will take which you want to transform the x1, x2, x3 into y1, y2, y3. So y transpose dy. So you can take it as the y, any one of the column matrix, y1, y2, y3. D, already we got the D from the 8th point, that is the diagonalization we got. Y we know, y transpose we know. If you multiply these three, you will get the required canonical form called lambda 1, y1 square, lambda 2, y2 square, lambda 3, y3 square. That is the required canonical form. See, very clear. It is a little bit lengthy procedure. Then x is equal to py. What transformation you are doing? So x is the given set of vectors x1, x2, x3. P is the orthogonal matrix. We have shown P inverse is equal to P transpose, and it means the columns of the each vector, columns of the each matrix here P1, P2, P3 that are orthogonal to each other x1, x2, x3. That's why automatically it became orthogonal. That's why our transformation is orthogonal transformation, right? So P inverse AP is equal to D, and using this P we are doing the transformation. X is x1, x2, x3. P is the orthogonal matrix. Y means y1, y2, y3. So finally we write what is the orthogonal transformation we have done from x1, x2 through y1, y2, y3. This is called a reduction of quadratic form to canonical form by orthogonal reduction. Now this is a procedure. Clearly I have explained step by step. In this step, in this procedure, we can reduce the problem. Right? Let us take a problem. So here I have given a quadratic form. How can we say it is a quadratic form? Reduce the quadratic form 3x square plus 2y square plus 3z square minus 2xy minus 2yz to the normal form by orthogonal transformation. See, it is a square terms and product terms. all are of the second degree homogeneous polynomial. So you can call it as a quadratic form. Now what they are asking, quadratic form to the normal form or canonical form by orthogonal transformation, because normal form another method also we can call it as canonical form by the orthogonal reduction. Now, so procedure just now we discussed. First of all, we need to convert the quadratic form to symmetric matrix A. Symmetric matrix for the given quadratic form. Write the square terms along the principal diagonal 3, 2, 3. Next, product terms, coefficient xy, coefficient minus 2, divide with 2, minus 1, minus 1. Next, minus 2yz. Xz is not there. At this position is xz, 0, 0. Next, yz, coefficient is minus 2, divide by 2, minus 1, minus 1. If any student get confused, then take this small chart which I explained earlier also, xyz, then you will understand the positions of the elements. X into x, x square, x into y, xy, x into z, xz. Multiply just simply. Y into x, xy, y into y, y square, y into z, yz. Next, z into x, xz, z into y, yz, z into z, z square. See, here the positions see clearly. X square, y square are square terms along the principal diagonal. Xy, xy, xz, xz, yz, yz. So according to that, I have written the coefficients divided by 2 and I have written. This is a clearly symmetric matrix. 3, minus 1, 0, 3, minus 1, 0. First row is equal to first column. Second row, minus 1, 2, minus 1, minus 1, 2, minus 1. Third column, 0, minus 1, 3. Third row, 0, minus 1, 3. So very clearly, A transpose is equal to A. Then it is symmetric. Okay, symmetric matrix. For this symmetric matrix, I need to find eigenvalues, eigenvectors, then I need to form orthogonal matrix, right? So we have discussed that clearly. Now to find eigenvalues, what to take? Characteristic equation. So the characteristic equation is det of A minus lambda I is equal to 0. Det of A minus lambda I is equal to 0 means how to write? Determinant, subtract the lambda from principal diagonal element. 3 minus lambda, minus 1, 0, minus 1, 2 minus lambda, minus 1, 0, minus 1, 3 minus lambda, which is equal to 0. We know very well how to write this one, and how to find the eigenvalues. We can expand the first row, or we have the formula lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. Where you need to find S1, S2, S3. S1 is the trace. In eigenvalues, eigenvectors topic and previous all lectures, we discussed very clearly. S1 is equal to trace of A, that is 3 plus 2 plus 3, 5 plus 3, 8. Next, S2. S2 means principal diagonal cofactors, that is 3, leaving this 3. 2, minus 1, 3. First principal diagonal, leave it, row and column, remaining 2, minus 1, 1, 3. Plus second principal diagonal 2, leave the 2 having column and row, that is 3, 0, 0, 3. Okay, now this element, leaving this column and this one 3, 0, 0, 3. Last third element, leaving this column and row, that is 3, minus 1, minus 1, 2. This S2 value. So that we can find the S2 value as 19. Simplifying this one, we can get S3 is equal to det of the matrix, that we can find expanding any one of the row. Here det is 12. Okay, S1, S2, S3. Finally, we get the equation lambda cube minus 8 lambda square, right, plus 19 lambda. Next, minus 12. So substituting S1, S2, S3 value in the equation. So that we are getting the eigenvalues, right? That is, we need to solve this third degree equation, third degree Cauchy polynomial, using scientific calculator or synthetic division. We can find the 3 roots. What are the 3 roots here? We are getting 1, 4, 3. So you need to solve this equation. We can check our eigenvalues are correct or not. Check the sum of the eigenvalues. The sum of eigenvalues is equal to 1 plus 3, 1 plus 4, 5, 5 plus 3, 8. See, our trace also matrix 8. So trace also 8. Trace is equal to sum. So your eigenvalues are correct. So whenever these two are equal, so this is a verification checkpoint. The some eigenvalues we are getting, we will be in confusion whether our eigenvalues are correct or not. So I gave very clearly one property of the eigenvalues. Sum of the eigenvalues is equal to trace of the given matrix, that is equal, then your eigenvalues are correct. What is the verification, right? Next, we need to find eigenvectors as well as lambda is equal to, we got 1, 4, 3 and corresponding eigenvectors. How to find the eigenvectors, that we have discussed very clearly. Eigenvector, that is a minus lambda I into x is equal to 0. So you need to substitute the lambda here and find out the eigenvectors. So since in eigenvectors topic and remaining previous topic also we discussed, here I am not explaining clearly what is how to find eigenvectors. In the previous videos you can find out, right? Here I am writing the eigenvectors corresponding to that 1, 4, 3. So for 1 you will be getting 1, 2, 1. For 4 will be getting the eigenvector x2, that is the 1, minus 1, 1, and x3 third eigenvector corresponding to 3, that is 1, 0, minus 1. So for lambda is equal to 1, 1 to 1, for lambda is equal to 4, 1 minus 1, 1, 1. You can verify these eigenvectors also, which can satisfy the equation a minus lambda I into x is equal to 0. Now let us write the modal matrix. But before writing the modal matrix, I need the norms of the vectors. Just now we discussed what is a normalized eigenvector. Now norm of x1. So under root 1 square plus 2 square plus 1 square, which is equal to root of 4 plus 2, 6. Next x2, norm of x2 under root 1 square minus 1 square 1 square, which is equal to root 3 second, and length of the norm of the third eigenvector 1 square plus 0 square plus minus 1 square, which is equal to root 2. So what is the modal matrix P, which contains x1 cap, x2 cap and normalized eigenvectors. It is not the ordinary eigenvectors. Normalized. Why? Because our transformation is orthogonal transformation. The matrix P must be orthogonal. So here x1 cap, you know very well, that is x1 by norm of x1, x2 cap, x2 by norm of x2, x3 cap, x3 by norm of x3. In the procedure I have explained very clearly. So now the modal matrix P. Okay. So how to write the P? Then in the x1 by norm x1. x1 element is 1 by. So here I am writing 1 by. It is divided with norm. What is the norm? Root 6. Next 2 by root 6. Each value of the x1 should be divided with its norm. 1 by root 6. Second one, x2 divided with its norm. x2 norm is root 3, divide with root 3. 1 by root 3 minus 1 by root 3. Next 1 by root 3. Third, x3 cap, x3 by norm x3. x3 is 1, 0 minus 1, whose norm is root 2. So then 1 by root 2, 0 by root 2, 0 minus 1 by root 2. So which becomes orthogonal. It is a orthogonal matrix. If it is orthogonal, then our transformation also becomes orthogonal transformation. Since P is orthogonal, P inverse is equal to P transpose. Orthogonal matrix property. P inverse is equal to P transpose. You no need to find the inverse. Just you transpose the matrix, it becomes inverse of the matter P. So that is because in our diagonalization we need P inverse. So here P inverse is equal to P transpose. Above matrix you transpose, that is 1 by first row as first column, 1 by root 6, 1 by root 3, 1 by root 2. Next, second row, 2 by root 6 minus 1 by root 3, 0. Second row, second column. Third row, 1 by root 6, 1 by root 3 minus 1 by root 2. So this is P inverse. So we got P inverse, and these using P inverse we can find, which is not ordinary model matrix, which contains orthogonal matrices, normalized orthogonal matrices. So the vectors here, these two product 0, these two product 0, and 1 and 3 0. You take any two vectors dot product, that will become 0. Definitely it will be orthogonal matrix. So that's why P inverse is equal to P transpose, okay, which is required for the diagonalization. So we determine eigenvalues, eigenvectors, and model matrix with the normalized eigenvectors. Now, so diagonalization. So in the procedure, we have explained diagonalization. Diagonalization formula, P inverse AP is equal to D. So we got in the previous slide, here we got the P inverse matrix is there, P matrix is there, and A is a given matrix. So that's why here I am writing P inverse and A matrix and P matrix. Right, all these three matrices. And earlier what we have, here you write P inverse here, right here given matrix, and multiply. On multiplying, clearly you will get the diagonal matrix. In the diagonal matrix, which are the eigenvalues? See, look at the previous slide. Here eigenvalues, what are the order we have taken? Same order we get. That is 1, 4, 3. And remaining definitely will be zeros. Okay. So you can check, you can use the calc mat A, mat B, mat C, enter in the three matrices in the calculator and multiply, you will be getting this product, which is a diagonal matrix. So P inverse AP is equal to D through orthogonal matrix, which is the orthogonal matrix P. Now, once the diagonalization completed, we got the D matrix, above matrix is D. 1, 0, 0, 0, 4, 0, 0, 0, 3, which is required for the canonical form. Actually, what is the canonical form? That is Y transpose dy is the required canonical form. What is Y? We have to take, let us say Y is equal to another set of values, variables Y1, Y2, Y3. Now, I want the canonical form Y transpose dy. What is the Y transpose? Column matrix will become row matrix, right? Y1, Y2, Y3. D, which we got through the diagonalization process using the orthogonal matrix, that is 1, 0, 0, 0, 4, 0, 0, 0, 3. D and Y. Y means Y1, Y2, Y3. Right? And multiplying 1 into Y1 into Y1. Y1 square plus Y2 into 4 into Y2. 4Y2 square. At a time we can't multiply, but directly we can say since remaining elements are 0, direct multiplication is possible. This into this into this. Plus Y3 into 3 into Y3. That is 3Y3 square. That is a required canonical form, which is sum of squares form. See, only squares, no product terms. This is canonical form. Again, here also we can say rank, index, signature, right? Okay. After finding this canonical form, we need one orthogonal transformation in the process. Orthogonal transformation. Through what transformation? We changed the values x1, x2, x3 to y1, y2, y3. That is called x is equal to py. So x means here we have x1, x2, x3, right? P we know, and y means y1, y2, y3, right? So that is first one 1 by root 6, 2 by root 6 and 1 by root 6. Second one 1 by root 3 and minus 1 by root 3. Next 1 by root 3. Next 1 by root 2. P matrix, earlier slide we have 0, 1 by root 2. So multiplying, that will be the orthogonal transformation. Here x1 is equal to, so row versus column, right? x1 into 1 by root 6 into y1, the 1 by root 6 y1 plus 1 by root 3 y2 plus 1 by root 2 into y3. This is orthogonal transformation. And x1 is transformed to y1, y2, y3, x2, here x2, second row into column, 2 by root 6 into y1, 2 by root 6 into y1, minus 1 by root 3 into y2, plus 0 into y3, that's leave it, 0 into y3, 0. Next x3, right, third row into column, 1 by root 6 into y1, next 1 by root 3 into y2, next 1 by root 2 into y3. This is orthogonal transformation. It is canonical form. So clearly we explained about the orthogonal transformation. The concept is here which matrix you are transforming, P. This P model matrix must be orthogonal. That is called orthogonal reduction. So clearly one quadratic form is given, we reduce to canonical form, which is called sum of squares form, right? So in this video lecture we have discussed about the reduction of quadratic form to canonical form by orthogonal transformation very clearly. In the next video lecture we will be having another procedure, that is reduction of quadratic form to canonical form by diagonalization. Why diagonalization required means sometimes the eigenvalues may not be the integers, then it is very difficult to find the eigenvectors and diagonalization. In that case we can use the diagonalization, and without finding eigenvalues and eigenvectors we can do the diagonalization. Simply we can do the quadratic form to canonical form without finding eigenvalues, eigenvector. That is in the next video lecture we discuss. That is at the end of the lecture. Thank you.